Imagine a star. A really, really big star, much bigger than our sun. These giant stars live fast and die young in cosmic terms, of course. When they run out of fuel, they can no longer support their own immense weight. The outer layers explode in a spectacular supernova. But what happens to the core, the very heart of the star? If this core is massive enough, gravity takes over with an unstoppable force. It crushes the core down, smaller and smaller, beyond anything we can truly comprehend. This relentless compression creates an object so dense, so gravitationally powerful, that nothing, absolutely nothing, can escape its grasp. Not even light, the fastest thing in the universe. This, my friends, is a black hole. It's not a hole in the traditional sense, it's a tremendous amount of matter packed into an incredibly tiny space. Think of it, the mass of several suns, or even millions or billions of suns squeezed into a region smaller than a city. This concentration of mass creates an escape velocity greater than the speed of light. Since nothing can travel faster than light, nothing can get out. It's the universe's ultimate prison, a one-way street to who knows where. Now let's talk about how these cosmic behemoths mess with the very fabric of the universe, space and time. Albert Einstein, a pretty smart guy, told us something profound with his theory of general relativity. He said that gravity isn't just a force pulling things together, like Newton thought. Instead, gravity is what happens when massive objects warp or curve the fabric of space-time. Imagine space-time as a giant trampoline. If you place a bowling ball in the middle, the trampoline sags, it curves. Now, if you roll a marble nearby, it won't travel in a straight line. It will curve inwards towards the bowling ball. Black holes take this warping to an unimaginable extreme. They are not just bowling balls on the trampoline, they are like an infinitely heavy object that has punched a hole right through it. The closer you get to a black hole, the steeper this curvature of space-time becomes. This isn't just a gentle slope, it's a precipice. So, what happens if you actually fall into a black hole? What's inside? This is one of the biggest questions in astrophysics, and the honest answer is, we don't definitively know. Our current theories, Einstein's general relativity and quantum mechanics, break down at the very center of a black hole. General relativity predicts a point of infinite density and zero volume called a singularity. Imagine all the mass of a star, or millions of stars, crushed into a point smaller than an atom. It's a place where the laws of physics as we understand them cease to make sense. Despite the mystery of their interiors, we've actually managed to see a black hole, or at least its silhouette. In 2019, the Event Horizon Telescope collaboration released the first ever image of the supermassive black hole at the center of the galaxy M87. And then, in 2022, they did it again, this time capturing an image of Sagittarius A*, the supermassive black hole at the heart of our very own Milky Way galaxy. Black holes come in a fascinating range of sizes, and when we talk about their size, we're usually referring to the radius of their event horizon, the Schwarzschild radius. The smallest black holes predicted by theory are primordial black holes, possibly formed in the very early universe, and they could be as small as an atom but contain the mass of a mountain. The smallest black holes we have actually observed are stellar mass black holes. Stellar mass black holes are the ones formed from the collapse of individual massive stars. They typically have masses ranging from about 3 to a few dozen times the mass of our sun. If our sun were to somehow become a black hole, its event horizon would only be about 3 kilometers in radius. A black hole with 10 times the sun's mass would have an event horizon radius of about 30 kilometers. These are incredibly compact objects. Section 5, the point of no return event, horizons and spaghettification. Let's talk more about that crucial boundary, the event horizon. Think of it as the ultimate point of no return. It's not a physical surface you could touch or stand on. It's a purely gravitational boundary in space-time. Once you cross the event horizon and head towards the singularity, there's no turning back. No matter how powerful your rockets, no matter what you do, your fate is sealed. The escape velocity from within the event horizon is greater than the speed of light, and since nothing can travel faster than light, escape is impossible. It's the edge of the observable universe from the inside looking out, and the edge of doom for anything falling in. Now imagine two observers. One is safely far away from the black hole. Let's call them Observer A. The other, Observer B, is bravely or foolishly falling towards it. As observer B approaches the event horizon, observer A would see some very strange things. Observer B's clock would appear to tick slower and slower due to gravitational time dilation. Their image would become increasingly redshifted, meaning the light waves get stretched out and appear redder. In fact, observer A would never actually see observer B cross the event horizon. Section 6. Cosmic Neighbors, Black Holes, Earth, and the Escape Question. You might be wondering, with all these cosmic vacuum cleaners out there, how do they affect us here on Earth? And is there any chance our planet could get gobbled up by one? Well, first, let's be clear, black holes don't go around sucking things up like a vacuum cleaner. They obey the same laws of gravity as any other object with mass. If our sun were to magically be replaced by a black hole of the exact same mass, Earth and the other planets would continue to orbit it just as they do now. We wouldn't suddenly get pulled in. The gravitational pull at our distance would be identical. We'd just freeze because, well, no more sunshine. The nearest known stellar mass black hole to Earth is called Gaia BH1, and it's about 1,560 light-years away. That's pretty far, cosmically speaking. Our solar system is not in any danger of encountering it or any other known black hole. The supermassive black hole at the center of our galaxy, Sagittarius A*, is about 26,000 light-years away. So you can sleep soundly tonight. A black hole isn't going to sneak up on us. Section 7. The Information Paradox, Encoding Secrets in the Dark. Black holes present some of the deepest puzzles in physics, and one of the most famous is the black hole information paradox. Here's the problem. Quantum mechanics, one of the pillars of modern physics, says that information can never be truly lost. Information about the state of a particle, for example, might get scrambled or rearranged, but it should always be recoverable, at least in principle. Now consider what happens when something falls into a black hole. It carries information with it, the type of particles, their energy, their quantum states. Once it crosses the event horizon, that information seems to be lost to the outside universe forever, trapped inside. This becomes a real headache when you consider Hawking radiation. As we just discussed, Stephen Hawking showed that black holes can evaporate. If a black hole evaporates completely, what happens to all the information that fell into it? Hawking's original calculations suggested that the radiation emitted is purely thermal, meaning it's random, and carries no information about what formed the black hole or what fell in. If this is true, then when the black hole disappears, all the information it consumed is gone forever, violating a fundamental principle of quantum mechanics. This is the paradox. General relativity says information is lost. Quantum mechanics says it can't be. Section 8. Beyond the Horizon, Holograms, Qubits, and Firewalls. The information paradox has pushed physicists to explore even more radical ideas about the nature of black holes and reality itself. One of the most profound concepts to emerge is the holographic principle. This principle suggests that the information content of any volume of space can be fully described by information encoded on the boundary of that region, like a three-dimensional image, a hologram, being encoded on a two-dimensional surface. Applied to black holes, it means that all the information about what fell into a black hole might actually be stored on its two-dimensional event horizon, not within its three-dimensional volume. Think about that for a moment. Everything that makes you, all the complex information in your brain and body, if you fell into a black hole, could theoretically be represented as a scrambled pattern on the event horizon. This idea has even been extended to the entire universe. Could our three-dimensional universe actually be a holographic projection of information stored on some distant two-dimensional boundary? It sounds like science fiction, but it's a serious theoretical possibility that physicists are investigating. It suggests that space-time itself might be an emergent property, arising from a more fundamental level of quantum information. Section 9. Unlocking the Universe. Why black holes matter for quantum computing and science. So, why do we spend so much time, energy, and brainpower studying these bizarre, distant objects? What's the payoff? Well, black holes are not just cosmic curiosities, they are crucial keys to unlocking some of the deepest mysteries of the universe. They are extreme laboratories where gravity and quantum mechanics collide. Understanding them forces us to confront the limits of our current theories and pushes us towards a more complete picture of reality, specifically towards that elusive theory of quantum gravity we talked about earlier. Such a theory would revolutionize our understanding of space, time, and matter at their most fundamental levels. The study of black holes, particularly the information paradox and concepts like the holographic principle, has profound implications for fields like quantum computing. Quantum computers aim to harness the strange laws of quantum mechanics like superposition and entanglement to perform calculations far beyond the reach of classical computers. The way information is seemingly processed, stored, or scrambled by black holes touches upon the very nature of quantum information. Understanding how nature handles information in such extreme gravitational environments could provide insights into building more robust and powerful quantum computers, or even reveal new principles of quantum information processing. Ultimately, studying black holes is about pushing the boundaries of human knowledge and satisfying our innate curiosity about the universe.